Welcome to another deep dive on G-Fun Facts Online. Today we are deconstructing one of the most fundamental concepts in physics, the behavior of liquids. For centuries, our understanding of the liquid state has been defined by a single, unshakable tenet, which is chaos. If you look at a solid, atoms are disciplined soldiers locked into rigid lattices. In a gas, they are anarchists flying apart. But a liquid is defined by constant, fluid motion. It is a bustling crowd where atoms jostle, slide, and flow past one another in an eternal, restless dance described by Brownian motion. This ceaseless movement is what gives liquids the ability to flow and take the shape of their container. Or at least, that is what we thought. In a discovery that has sent shockwaves through condensed matter physics and materials science, researchers have unveiled a phenomenon that theoretically should not exist. They call them anchored atoms. Deep within the molten churn of liquid metals, scientists have observed particles that defy all known rules of liquid dynamics by simply refusing to move. These atoms stand stoic and still, anchored in place while their neighbors rush past them in a superheated frenzy. This is not merely a curiosity, it is a violation of our intuition about how matter behaves. These immobile particles do not just sit there, they actively dictate the behavior of the liquid around them, trapping swirling atoms in atomic corrals and preventing liquids from freezing even when temperatures plummet. Today we are going to explore the atomic scale experiments that revealed these ghosts in the machine, the quantum mechanics that allow such a paradox to exist, and how this discovery, along with other fluid anomalies like negative mass fluids and shape-recovering liquids, is rewriting the textbooks. Let us start with the discovery itself. It did not happen in a massive particle collider, but on the glowing screen of one of the world's most powerful microscopes. The discovery emerged from a collaboration between the University of Nottingham in the UK and Ulm University in Germany. The team, led by Professors Andrei Klobostov and Ute Kaiser, was investigating the solidification processes of metal nanoparticles. Their goal was to understand how molten metals like platinum, gold, and palladium transform into crystals as they cool. To do this, they placed nanoscopic droplets of these metals onto a sheet of graphene, which serves as the ultimate petri dish for atomic observation. Using the Salveia instrument, or sub-angstrom low-voltage electron microscopy, a tool capable of visualizing individual atoms without destroying them, they heated the metals until they melted. The expectation was standard. As the heat rose, the metal's crystalline lattice should collapse, and the atoms should dissolve into a frenetic, incoherent blur of motion. Professor Klobostov noted that atoms in liquids typically move in a complex way, constantly and rapidly passing by each other. But that is not what they saw. As the metal melted and the majority of atoms began their high-speed chaotic swirling, a subset of atoms remained eerily still. They were effectively immobile. In the video feeds from the electron microscope, these atoms appeared as bright, stationary pillars amidst a river of flowing grayscale. They held their ground, even as the temperature soared hundreds of degrees above the metal's melting point. It was as if someone had placed a rock in a stream, but in this case the rock was chemically identical to the water. This challenges the fundamental definition of a liquid, where every atom should be equivalent. The existence of a caste system of atoms, some free to roam and others shackled in place, suggested that the liquid state is far more complex than we imagined. So why were they stuck? The answer lay in the graphene substrate. While graphene is often touted as a perfect honeycomb lattice of carbon, real-world materials have imperfections. The graphene sheets contained tiny point defects where a carbon atom was missing or altered. The researchers discovered that the metal atoms were forming a unique, ultra-strong bond with these defects. The interaction was so potent that it overcame the thermal energy trying to push the atom into motion. The defect acted as a microscopic anchor, pinning the metal atom to the floor of the droplet. Crucially, the electron beam used to observe the sample played a role in creating these defects. By tuning the intensity of the beam, the scientists realized they could effectively write anchors into the material, determining how many atoms would get stuck. They had stumbled upon a way to remotely control the atomic freedom of a liquid. The presence of a few stationary atoms acted as powerful disruptors through a mechanism known as geometric frustration. In a normal cooling process, a liquid turns into a solid when a seed crystal forms. A few atoms lock into a pattern, and that pattern spreads rapidly through the liquid like a wave. However, the anchored atoms blocked this wave. When the liquid metal tried to align itself into a crystal lattice, it would bump into an anchored atom that was in the wrong spot. The lattice could not grow around it. The anchored atoms effectively confused the liquid, preventing it from organizing. The most spectacular consequence of this was the creation of atomic corrals. When the anchored atoms were arranged in a circle or a dense cluster, they trapped a pool of liquid metal inside them. Because the anchored atoms prevented the crystallization wave from entering the corral, the liquid inside remained liquid far below its freezing point. For context, the normal melting point of platinum is 1768 degrees Celsius. However, inside these corals, the platinum remained liquid at temperatures as low as 350 degrees Celsius. That is a staggering difference. Imagine water that stays liquid at negative 100 degrees simply because a few ice cubes are glued to the bottom of the glass in a specific pattern. This state represents a hybrid state of matter, a solid stabilized liquid. The atoms inside are free to move and flow, retaining all the catalytic and chemical properties of a liquid, but the overall droplet is held in a fixed shape by the skeletal framework of the anchored atoms. This forces a revision of classical nucleation theory, which assumes that the birth of a crystal is a random process driven by temperature and pressure. The anchored atom phenomenon introduces the variable of topological confinement, suggesting that the geometry of the boundary is just as important as the temperature. Now, to understand the magnitude of this discovery, we must place it in the context of other rebel fluids that have recently been discovered. The anchored atom is part of a universe of anomalous fluids. Just months prior to this understanding, researchers at the University of Massachusetts Amherst discovered a liquid that defies gravity and entropy, known as the shape-recovering liquid or the immortal droplet. They were working with a mixture of oil, water, and magnetic nanoparticles. Typically, if you mix oil and water and shake them, they separate. However, when doped with magnetic nanoparticles, the droplet formed a specific shape. When they destroyed the shape by smashing or dispersing it, the liquid reassembled itself back into the original shape the moment the interference stopped. According to the second law of thermodynamics, systems tend toward disorder. A smashed droplet should not spontaneously put itself back together. The explanation was that the magnetic particles formed a jammed layer at the interface, creating a flexible armor that stored the energy of the shape. Then there are negative mass fluids. At Washington State University, physicists created a fluid composed of rubidium atoms cooled to near absolute zero that exhibited negative mass. When the researchers pushed this fluid with a laser, it accelerated backwards, moving toward the push. This quantum phenomenon inverts standard Newtonian mechanics. And of course, we have frictionless superfluids like helium-4, which when cooled, lose all viscosity and can flow forever. Anchored atoms represent the opposite extreme of superfluidity. In a superfluid, atoms are so coherent, they flow without resistance. In the anchored state, atoms are so incoherent due to the trap that they refuse to flow at all, yet allow the surrounding medium to remain fluid. Both show that the liquid state is a spectrum of quantum possibilities. Why does this matter for technology? The ability to pin atoms in place turns a liquid from a chaotic mess into a programmable tool. The most immediate application is in catalysis. Catalysts speed up chemical reactions and are essential for refining oil, cleaning exhaust, and producing fertilizer. The most effective catalysts are expensive metals, like platinum. Solid catalysts are inefficient because only the surface atoms interact. Liquid catalysts are hyper-efficient but unstable and require extreme heat. The corralled supercooled liquid offers the best of both worlds. It is a liquid, so the atoms are mobile and active, but it is trapped by anchored atoms, so it is stable. And it stays liquid at 350 degrees instead of 700 degrees. Imagine a chemical plant that runs at half the temperature, uses 90% less platinum, and produces zero waste because the catalyst is a self-healing liquid. This could revolutionize hydrogen fuel cell production. Beyond that, we are looking at atomtronics, machines built at the atomic scale. Anchored atoms provide a method for bottom-up assembly. By using an electron beam to create defects in graphene, we could draw a blueprint of anchors and pour liquid metal over it. The metal would solidify only where we want it to. This could allow for atomic wires only a few atoms wide, quantum dots for solar panels, and self-repairing circuits that heal breaks because they remain fluid. There are also implications for phase change memory devices. Computers store data in ones and zeros, often switching between crystalline solids and amorphous glasses. The anchored atom effect provides a new way to control this switch using electric fields to engage anchors, potentially leading to memory storage faster than RAM and permanent like a hard drive. Theoretically, this discovery breaks the ergodic hypothesis in statistical mechanics, which states that a liquid system will eventually explore all possible states. Anchored atoms violate this. The system is non-ergodic. It also provides a toy model for the glass transition mystery, explaining why some liquids turn into glasses rather than crystals. It suggests glass formation might be driven by random pinning sites. We are witnessing a shift from observing material properties to dictating them. For history, we accepted that iron melts at 538 degrees. The discovery of anchored atoms tells us that the melting point is a negotiation between atoms and their environment. By intervening in that negotiation, we can create materials that defy natural instincts, like room temperature liquid metals for flexible robotics, or tunable solvents that switch from liquid to solid on command. The image of the anchored atom, a sphere held fast against the tide, is the symbol of the next age of materials science. The immobile particle does not just defy liquid dynamics, it defines the future of them. Thanks for listening to this episode of G Fun Facts Online.